we will recapitulate first what we have done in the earlier two lectures. We have first talked about the stress at a point. It is indicated by sigma ij. It is a 9 component tensor for 3 dimensions and it has 4 component for 2 dimensions. And we have also seen that this tensor is symmetric, thereby we can indicate it in the following form: sigma ij equal to sigma ji. Similarly, we have introduced the strain tensor, which is also a tensor having 9 components for 3 dimensions and 4 components for 2 dimensions. It is also symmetric tensor, therefore epsilon ij equal to epsilon ji. We have also seen that there is a difference between engineering shear strain and tensor shear strain. Engineering shear strain is twice the tensor shear strain. Specifically, we have seen gamma 12 is equal to 2 times epsilon 12. Similarly, same relationship, same type of relationship holds good for gamma 23 and gamma 31. We have then defined the strains at a point in terms of the 3 displacement components u, v and w. These are the Cartesian components of displacements of a point on the body, and we have seen that epsilon x is nothing but epsilon 11. It is given by the partial derivative delta u delta x. Similarly, epsilon y is nothing but epsilon 22. This is given by delta v delta y, and epsilon z, which is nothing but epsilon 33. This is given by the partial derivative of w with respect to z. Then we have seen the shear strains. Shear strain, if it is gamma xy, which is nothing but gamma 12, this is given by delta u delta y plus delta v delta x. Similarly, gamma yz is equal to gamma 23, which is nothing but delta v delta z plus delta w delta y. Lastly, we had gamma zx is equal to gamma 31, which is nothing but delta w delta x plus delta u delta z. You have also noted that this component is equal to 2 times epsilon xy. This is 2 times epsilon yz, and this is also 2 times epsilon zx. Then we took up the calculations of tractions on an arbitrary plane. So, traction component on an arbitrary plane where the stresses are given by sigma ji, and if the arbitrary plane has direction cosines Lj, then in that case we have seen that Si is nothing but Lj sigma Ji, wherein Si are the components of traction, and in this we have made use of the implied condition that I takes up value 1, 2, 3, so also J takes up value 1, 2, 3. This indicates compact form of expanded expressions, and herein we make use of the fact that these two symbols are repeated, therefore a summation is indicated. So these two symbols are repeated and it indicates a summation. Just to give one case, S1 is nothing but L1 sigma 1 1 plus L2 sigma 2 1 plus L3 sigma 3 1, herein I is fixed here, this is fixed, and L is varying from 1 to 3, so also the stress components are varying 1, 2, 3. Now we would like to take one example. First we would like to consider the calculation of strain at a point. Of epsilon ij it is given that in a body which is undergoing deformation, a point P has displacement given by the vector I into x square minus yz plus j 2y minus xz square plus k into 3z minus x square y square this multiplied by 10 to the power minus 3 millimeter. So the displacements are given in millimeter. Herein I, j and k are the unit vectors in the three Cartesian directions. Therefore, you should have no difficulty in identifying that the x displacement of the typical point is given by x square minus yz, and v displacement is equal to 2y minus xz square, and w is given by 3z minus x square minus y square, and all these expressions are multiplied by 10 to the power minus 3 . So these are the displacements. Now using these displacements, we would like to now calculate the strains strain components particularly. So if I now consider epsilon x, this is given by delta u delta x. So this will be given by twice x multiplied by 10 to the power minus 3. So this is millimeter by millimeter. So strains are dimensionless. So henceforth I will not show the units. Epsilon y delta v delta y, this is given by 2 10 to the power minus 3 and w is equal to w epsilon sorry, the strain components epsilon z delta w delta z is equal to 3 multiplied by 10 to the power minus 3. Similarly, we can calculate the shear strains gamma xy delta u delta y plus delta v delta x. So this is given by minus z minus z square into 10 to the power minus 3 gamma yz delta v delta z plus delta w delta x. So this is going to be given by minus 2 xz minus 2 xy square this should be delta w delta y. So it should be 2 x square y. So 2 x square y and gamma zx is nothing but delta w delta x plus delta u delta z. This is given by minus 2 xy square and this is minus y into 10 to the power minus 3. Here also you will have a multiplier 10 to the power minus 3. If it is given specifically to calculate the strains at a point, the point P coordinates are given as 2, 3, 4 in millimeters unit. So if we now substitute the value of these coordinates, then we get the following strains. Four minus 20 minus 39 minus 20 2 minus 40 minus 39 minus 40 3, and all these have a common multiplier 10 to the power minus 3. This is millimeter by millimeter. So these are the engineering strains at the point P with coordinates 2, 3, 4. If we want the tensor components, it is going to be 4. This will be half of what we have here. So, it is 10 minus 19.5 minus 10, 2 minus 20 minus 19.5 minus 20, 3 multiplied by 10 to the power minus 3. This is the strain tensor at point P. We would like to consider one example, calculation of tractions. Given the stress tensor at a point like this, hundred 0 0 0 200 0 0 400, these are these stresses at a point. Now, it is necessary to calculate the tractions SI on plane with direction cosines point 707, 0.707 0. This means, so a solution can be done like this. We have L1 is nothing but 0.707, L2 0.707 and L3 is equal to 0. So, these are the direction cosines, and therefore, we can now calculate the traction component 1, which is given by L1 sigma 11 plus L2 sigma 21 plus L3 sigma 31. Herein L1 is 707 and the sigma 11 is 100, then L2 is also 7.707 and sigma 21 is 0 and this L3 is 0 and sigma 31 is 0. So, therefore, it gives us value like 70.7 MPa. So, that is the traction in the direction 1, and it has the same units as the stress. You can calculate similarly the tractions for the other two directions. S2 is given by L1 sigma 12 plus L2 sigma 22 plus L3 sigma 32, and if we substitute the value, it becomes 0 0. This is 707 multiplied by 200 0 multiplied by 0. So this gives us 141.4 MPa. Now S3 is given by L1 sigma 13 plus L2 sigma 23 plus L3 sigma 33. Here L1 0.707, sigma 13 is 0, this is 707, this is 0, and this is 0 multiplied by 400, so therefore this is 0. Please note that this value should not be 0, it should be 0.707. So this amendment you can note, but the value of S2 does not change. So the three traction components are, finally we have S1 is 70.7 MPa, S2 is 141.4 MPa, S3 is 0. So these are the three traction components on the plane whose direction cosines are 0.707, 0.707 and 0. Now we would like to consider determination of principal planes and principal stresses. So determination of principal stresses and principal planes. Do you remember what is principal stress? These are the stresses which act on plane where there is no shear stress. So we would like to now consider determination of such stresses in 3 dimensions. So we have the stresses at a point given by sigma ij, and we would like to find out the stresses which are acting on planes where there is no shear stress. So we are interested in determining the stresses like, let us say, sigma 1 and its direction cosines L, M and N. So we will indicate the principal stresses by symbol, just indicate by sigma. So sigma is the principal stress and it is acting on a plane with direction cosines L, M and N, and this plane is such that there is no shear stress. So shear stress on this plane equal to 0. So we are really interested in determining this set where there is shear stress equal to 0. Now we try to consider one plane A, B, C. Let us say this is the plane whose outer normal is directed like this. This is the outer normal. Let us assume that this is the plane which has direction cosines L, M and N, and therefore on this plane we have a stress sigma acting, and this plane ABC is devoid of any shear stress. Now, if I make use of the Cauchy formula, then the traction components we can obtain. So, we will like to write the traction components here. So, these are the 3 traction components for this plane. This is Sx, this one is Sy, and this component is Sz. So, we can write now Sx is equal to L sigma x plus M tau yx plus N tau zx. Similarly, Sy L tau xy M sigma y plus N tau zy. Sz is equal to L tau xz plus M tau yz plus N sigma z. These are the tractions on this plane ABC. Let the area of this plane ABC be represented by the symbol A. Now, the force which is going to act in the x direction because of the stresses on this plane is going to be nothing but A into Sx, and we can also find out the component from the stress sigma. The total normal force on this plane is nothing but L sigma into A. Its component, total force on this plane ABC is nothing but A into sigma, and its component in the x direction is L sigma into A. So, therefore, we can write that the total force in the x direction is nothing but Ax, and this should also be equal to A into sigma multiplied by A. So, finally, we get Sx is equal to L into sigma. Similarly, you can have consideration of force in the y direction, thereby you will find that Sy is nothing but M into sigma, and Sz is equal to N into sigma. Now, we will substitute the value of Sx, Sy, Sz in terms of sigma. So, if I do that, we finally get the following, that L sigma x minus sigma plus M tau yx plus N tau zx equal to 0. So, what I have done is that I have coupled these relationships Sx and this Sx and simplified. Similarly, we get from the second expression M sigma y minus sigma plus n tau zy equal to 0. Similarly, L tau xz plus m tau yz plus n sigma z minus sigma equal to 0. This set of equations, let us represent it by set 1. Now, it is a homogeneous set of equations with unknown L, M and N, the direction cosines of the plane, and if we have to have solutions for non-zero solutions for L, M and N, it is necessary to have this condition satisfied. Determinant of the coefficient matrix, which is nothing but sigma x minus sigma tau yx tau zx tau xy sigma y minus sigma tau zy tau xz tau yz sigma z minus sigma. So, this determinant must vanish. So, it should be equal to 0. So, this is the characteristic equation. This equation can be written in tensor notation. Particularly, we can use also the tensor notation to represent equation number 1 in the following form, that Lj sigma ji minus Lj delta ji into sigma equal to 0, where this delta ji is nothing but Kronecker delta. Kronecker delta. This Kronecker delta has the characteristics that delta ji is equal to 0 when I is not equal to j, and it is equal to unity when I equal to j. So, with those implications, we can write the equation number 1 in this form. So, this is really the form of equation number 1. So, we will indicate equation number 1 dash. Similarly, the equation number 2 is nothing but determinant sigma ji minus delta ji into sigma equal to 0. So, this is in a compact form we can write it. So, we have seen that the equation number 2 can be written in tensor form like this. If we go back to the original form of equation 2, this can be expanded and we will get an equation in sigma, which is of this form: sigma cube minus I1 sigma square minus I2 sigma minus I3 equal to 0, where these coefficients I1, I2 and I3 are given in terms of the stresses. I1 is equal to sigma x plus sigma y plus sigma z, and I2 is tau xy square plus tau yz square plus tau zx square minus sigma x minus sigma y minus sigma y minus sigma z minus sigma z into sigma x. Similarly, I3 is given by sigma x into sigma y into sigma z plus 2 into tau xy tau yz into tau zx minus sigma x into tau yz square minus sigma y tau zx square minus sigma z into tau xy square. So, these are the coefficients, these are called stress invariants. I2, I3 are known as stress invariants. This equation will have 3 roots for sigma, and it can be shown that these roots are real. Let us say the 3 roots are sigma 1, sigma 2 and sigma 3. If these 3 roots are distinct, then they are going to work on 3 mutually perpendicular planes. So, for 3 distinct roots, will have 3 directions which are going to be mutually perpendicular. So, if we consider the directions of the 3 stresses as Lj1 for the sigma 1 stress, Lj2 for the sigma 2 stress and Lj3 for the sigma 3 stress, then these 3 directions are going to be mutually perpendicular. So, these are 3 mutually orthogonal directions. If we have a situations like that sigma 1, there are 2 repeated roots, sigma 1 equal to sigma 2, but then that is not equal to sigma 3, then we can find out this sigma 3 directions, and then Lj1 and 2 can be taken as any 2 directions on the plane perpendicular to Lj3. So, Lj1, Lj2 which corresponds to sigma 1 and sigma 2, they will be any 2 directions, any 2 directions on plane perpendicular to Lj3. If we have 3 roots repeated, if we have sigma 1 equal to sigma 2 equal to sigma 3, then any 3 orthogonal directions are principal directions. Now we can find out the roots of this equation 3 easily. So we can solve the equation. So solution of equation 3, we can solve this cubic equation by following the following steps. In fact, we can write sigma 1 to be given by I1 by 3 plus 2 minus A by 3 cosine phi. Sigma 2 is I1 by 3 plus 2 times A by 3 cosine 120 degree plus, I am sorry, it should be phi by 3, and this is also phi by 3, and sigma 3 is equal to I1 by 3 plus twice minus A by 3 cosine 240 degree plus phi by 3, where we have A is given by minus I2 plus I1 square by 3, and we have cosine phi is equal to minus b by square root minus a cube by 27, and this b is given by minus I3 plus 2 I1 cube by 27 plus I1 I2 by 3. So the solution for the equation in cubic equation are given by these expressions, wherein all these constants A, phi and B are related to the stress invariance. Let us understand why stress invariance. So we have found that the quantities like I1, I2 and I3 are stress invariance. You should have no difficulty in appreciating that when a body is loaded, its deformation will take place, and at a point there will be principal directions. There will, at each point there will be 3 principal directions, and these principal directions are fixed. So long as the loading on the body is fixed, the principal directions are fixed directions. That means the 3 directions LJ1, LJ2, LJ3, which corresponds to stresses sigma 1, sigma 2 and sigma 3, they are fixed, and they are dependent on the stress tensor at the point. Now, the direction of these principal stresses are fixed at a point. This will not depend on the selection of coordinates for defining the stress tensor. So, this stress tensor sigma ji is going to depend on selection of the coordinate x, y, z, but the value of the principal stresses and their directions are fixed, which implies that the cubic equation that we had written a little while ago, that sigma cube I1 sigma square minus I2 sigma minus I3 equal to 0, the roots of these equations must be unique. It will not depend on the selection of coordinates. If 2 persons are selecting 2 different coordinates, it is going to probably have values of sigma ji for one person, and for another person it may have value sigma ji dash, but these 2 situations must lead to a equation in sigma which should not depend on the coordinates. Therefore, this I1, I2, I3 must be independent of the coordinates. So, I1, I2, I3 independent of coordinates. That is why they are called stress invariants, and you can therefore finally write that the value of I1, which is given by sigma x plus sigma y plus sigma z, it must be also equal to sigma x dash sigma y dash plus sigma z dash. So, also we will have I2 given by tau xy square tau yz square plus tau zx square minus sigma x sigma y minus sigma y sigma z minus sigma z sigma x. This should also be equal to tau xy dash square tau yz dash square plus tau zx dash square minus sigma x dash sigma y dash plus, I am sorry, this should be plus sigma y dash sigma z dash plus sigma z dash sigma x dash. Similarly, we can write the third stress invariant also along similar lines, sigma x, sigma y, sigma z plus twice tau xy, tau yz, tau zx minus sigma x, tau yz square plus sigma y into tau zx square plus sigma z tau xy square. It is also equal to sigma x dash, sigma y dash, sigma z dash plus twice tau xy dash, tau yz dash, tau zx dash minus sigma x dash square, xj sigma x dash tau yz dash square plus sigma y dash into tau yz square plus sigma z dash into tau xy dash square. So, the expression for the quantities I1, I2, I3 are going to come to the same value. That is why they are not dependent on the coordinates, and it is because of this reason they are called stress invariants.